Welcome back. This is part B of concept video for section 16.2 line integrals. So in the last video, part A of the video, we defined what the definition of line integral was, how to evaluate, and then how we can even find out the arc length with the help of the line integral definition, and so on. So now, line integrals along C with respect to x, y, and z can also be defined. For example, integral over C, f of x, y, z, dz. Earlier we said ds. S was the arc length. ds was the arc length. Here dz, just limit is n approaching infinity, sigma, f of xi star, yi star, zi star, delta zi in terms of Riemann sum. The Riemann sum can be converted to an integral. So it's integral a to b, f of x as a function of the parameter t, x of t, y of t, z of t. Then this dz, z as a function of t, z equal to z of t. So dz would become z prime t dt. So you get z prime t dt for this part. So it is integral a to b f of x of t, y of t, z of t times z prime t dt. Therefore, as with the line integrals in the plane, we evaluate integrals of the form integral over Cp of xyz dx plus q of xyz dy plus r of xyz dz by expressing everything x, y, z, dx, dy, dz, everything in terms of t. So just the way we defined z as a function of x when x is treated as a function of t, the parametric form, then dx would be replaced by x prime t dt. Same thing with y. Here remember f is a lowercase f is always a scalar function. Uppercase f will be taken as a vector field. Define the line integral of a vector field f along a smooth curve C given by a vector function R of t. Curve C is written by R of t. The space curve is written as a vector function R of t. If f is a continuous vector field and C is given by the vector function R of t, where t lies between a and b, then integral over C f dot dr can be written as integral. We are going to convert everything to t. So the variations for t is integral a to b f of r of t, then dot dr would be r prime t dt, which in turn can be written as integral over c f dot tangent t ds. You know that t can be written as r prime t over length of r prime t. So we can write this part as r prime t dt as t ds, which is nothing but the tangential component of f. Work done in moving a particle along C can be interpreted in terms of line integral. So it is W equal to integral over C f of xyz dot t of xyz ds. So it is taking this part, which is integral over C f dot t ds. Thus the work done is a line integral with respect to the arc length of the tangential component of the force, because it's f dot t. Let's see, it is the tangential component of the force, and it is in line integral is with respect to the arc length, which is ds. If F is a force field, what does this line integral represent? So the line integral represents, if the vector field is the force field, then the line integral would represent the work done. Work done by the force F in moving the particle, in moving a particle along the curve C. So the formula that we defined earlier, line integral for any vector field, in particular, if this vector field happens to be the force field, then line integral, there is no difference between the line integral and the work done in moving the particle along the curve C. If the vector field F has components P, Q, R, I component, J component, and the K component, what is the connection between the line integral of F and the line integral of the component functions P, Q, and R? Integral over C F dot dr equal to integral over C. So we can write F as P, Q, R in the component form. And then dot dr we can write in the component form as dx, dy, dz. So we can write this dot product as integral over C. If you multiply the corresponding components, it's p dx plus q dy plus r dz. The dot product of two vectors, you multiply the corresponding components and add. So line integral f dot dr, integral over c f dot dr, can also be written as integral over c p dx plus q dy plus r dz. As I said earlier, you can check these problems. Problem number 15, problem number 21, problem number 39, and also problem number 3. All these problems are done in the section videos for section 16 too. Please refer to these problems in the videos for section 16 too. For this video, we will show one example. Let's pick problem number 7. Evaluate the line integral where C is a given curve. Integral over C, x plus 2y dx plus x squared dy, where C consists of line segments from 0, 0 to 2, 1 and 2, 1 to 3, 0. So C is made up of two line segments. One is connecting the origin to 2, 1. The second one is connecting 2, 1 to 3, 0. What we are evaluating is integral over C, x plus 2y dx plus x squared dy. If you notice its representation, it is of the form p dx plus q dy. So from what we learned, integral over c p dx plus q dy is nothing but integral over c f dot dr, which is the line integral in 2 dimensions. So let's do this problem here, right below. Let's consider this line integral p dx plus q dy. So the given integral is the line integral. We'll call it I. It is of the form f dot dr, integral f dot dr, where f has components p and q, which are x plus 2y and x square, and dr has components dx, dy. So this is nothing but the line integral. line integral over C. So now we have to write this integral as sum of over sum of two curves. So the curve C is made up of two line segments C1 and C2, where C1 is the line join of 0, 0 and 2, 1. And C2 is the line join of 2, 1 and 3, 0. So we have to parameterize. So we need to parameterize C1 and C2, or reduce the number of variables. So 0, 0 to 2, 1, line join of 0, 0 to 2, 1. So slope for that curve, for that line segment is difference in y over the corresponding difference in x. So it is 1/2. So as the line passes through the origin, so it is going to have the equation y equal to half x. So y equal to half x. So how do I parameterize it? I'm going to write x as t, and then y equal to half of t. If x is t, y is half of t. That is the parameterization of the first curve, which is the line join of 0, 0 and 2, 1. And for the curve, for the line C2, let's say line segment join 2, 1 and 3, 0, the slope is difference in y over the corresponding difference in x. So it is going to be -1 over 1. So it is just -1. So if I use the point slope form, y minus y1 equal to m times x minus x1. It becomes y equal to -x plus 3, or 3 minus x. Here, if I plug in x equal to t, then y will become 3 minus t. That way I'm parameterizing both the first curve and the second curve. Of course, I have to remember to give the values for t. In the first one, it is a line join of 0, 0 to 2, 1. So I'm keeping x equal to t. I'm keeping x equal to t. So the parameter t are the variations for x. So here, for the first curve, the variations would be 0 less than or equal to t, less than or equal to 2. And then for the second curve, again, I'm keeping x equal to t. So the variations for t would be the variations for x in the second curve. The variations for x would be from 2 to 3. So t runs from 2 to 3. So now the next step is to evaluate the integral. The evaluate the integral is the third step. When you evaluate the integral, what you are doing is you are integrating integral over c x plus 2y dx plus x square dy is integral over c1, same thing, x plus 2y dx plus x square dy plus integral over c2, same thing, same integrand, x plus 2y dx plus x squared dy. Only the line segments have different parameters, the same parameter t, but different values for t. So we have to be careful when we substitute them and evaluate them. So for the first C1, as we said, C is made up of the two curves C1 and C2. That's why we are splitting the integral C into C1 plus C2. The integral over C1, the parameter runs from 0 to 2. So we we will substitute that 0 to 2. Then we will also assume x equal to t, then 2 times y equal to half of t for C1. So it is half of t dx. What is dx here in C1? If x is t, dx would be automatically dt. So dx would be dt plus x square, so which is t square, dy. So from here in this one, dy would be half of dt. So I'm going to substitute for dy, which is half of dt. We got that. Plus C2. For C2, the t variation is from 2 to 3. X equal to t plus 2 times y. For C2, y equal to 3 minus t. Dx is same as dt plus x square, which is t square. For the second curve, dy equal to negative dt. Derivative of 3 is 0, so negative dt. So this will be negative dt. So it is dy is half dt here, then dy is negative dt here. Now, if we expand this, it's integral 0 to 2. So it is going to be t plus t dt, which is equal to 2t dt plus t square over 2, everything dt. I'm combining all the dt's. So the first one is t plus t dt plus t square dt, half of t square dt, integral between 0 to 2. Then for the second one, it is integral 2 to 3. This will be 2t plus 6 minus 2t. Then we have minus t square. So if I simplify, I'll have 6 minus t square dt. The rest is only a simple integration. So integral over c, line integral would be 2t square over 2 plus half of t cube over 3 between 0 and 2 plus 6t minus t square over 2 minus t cube over 3 between the limits 2 and 3. So if you plug in these limits for the upper and the lower and then evaluate and then expand and simplify, then you will get the value of the line integral to be equal to 5 by 2. So it is integral over c x plus 2y dx plus x square dy equal to 5 over 2. Hope this video helps. In my next video, I'll be showing you concepts from 16.3. Make sure to watch that video.